today, cyclic quadrilaterals. A cyclic quadrilateral is any four-sided figure that can be drawn where all its edges are touching a circle. And the fascinating thing about that, years ago when we had heaps and heaps of time, got the compasses out, draw them all, draw any random measure. The diagonally opposite angles always added up to be 180 degrees. Now that is a property. So if I just give you a random four-sided figure and it's not drawn in a circle, and I say this is a cyclic quad, bang, you can assume the diagonally opposite angles add up to be 180. Happy? If I ask you, is this four-sided figure a cyclic quad, what would you have to do? Prove that the opposite, or test that the opposite angles add up to be 180. It's that simple. Do we agree? Okay, so don't worry about that. We can jump straight to this. So number 3, how would we find x? 180 minus 73. Why? Because it's a cyclic quad, because the four edges touch the circle. If this vertex here did not touch it, then we were stuffed and we can't do it. So we're not actually going to go and do these because that's a waste of our time. Agreed? What about B? Joe, what do you know? How would I do this? We notice four edges touch the edge of the circle. Haha, it's a cyclic quad. Therefore, the diagonal angles add up to be 180. So we would write down x plus 2x must equal 180. Why? CQ, cyclic quad. Yep.
If all sides touching, you just say that in your evidence.
You just go, it's a cyclic quad. You don't have to say the four sides touch. You just put in your brackets CQ, cyclic quad. We will do proofs in a minute and you'll see exactly what goes on. Okay, what about C? All right, so let's put heading, cyclic quad, today's date. We will actually do this one. At the moment, because we're doing this little section on cyclic quads, you're going, yeah, 180. Remember, when this is all mixed up, you might have a triangle somewhere too. You have to look. And as soon as we are seeing these little edges, we're going, yeah, baby, cyclic quad. But we also notice something else. What did you say, Nails?
The lines are parallel.
Right, we've got parallel lines. So on first inspection, we go, well, I don't have any of the diagonally opposites, so I can't just say that plus that equals 180, can I? So what does it mean with your parallel lines? How can I use them? Excellent, Rian, excellent. Although they are on your sheet as well, my friend. They are on that sheet. Where's your sheet? Yep, first page. Sure, but I would be going, I'd be going co-interior. So we know that we've got alpha and beta. So alpha plus beta equals 180. How does that help us here? What would be the easiest one to put? Yeah, so what is this? Hello, what is this? 180 minus alpha, right? Here's my parallel lines. It means that this plus this has to add up to be 180. So if that's already x, that's got to be 180 take x. Do we agree? And now we can go on our merry way. So we're going to say angle ADC equals 180 minus x and y. Remember, do not tell me parallel lines. It's got to be, yes, co-interior. Yeah. I always say supplementary or allied, but anyway, I'm sticking with allied. You can put co-interior. Anyway, and therefore, we can now say that, should have done it a bit nicely, so angle ABC, angle ABC, oh geez, going too fast, ABC plus angle ADC equals 180 degrees. Y, cyclic quad, CQ, baby, CQ, cyclic quad. If you want to write cyc quad, go for it. If you want to write the whole thing, love it. And therefore, 2x minus 70 plus 180 take x has to equal 180. Huzzah, huzzah. X equals 70. Happy days? What have we got happening there? Wait, I want everyone to have a think, and then I might just randomly pick somebody. So yes, no prizes for guessing yes, it's a cyclic quad because all the 4 edges are touching. But what's going on with this bit here? No. No. Overthinking. Okay, who would like to? Anyone? Yeah, you go. You go. There's no triangle, no. Think even simpler. Pardon? Collinear. Yeah, straight line. So because we've got this, we've got a straight line here. What do we know about a straight line? The angles add up to be 180. So I think some of you were going, it cannot be that simple. There's got to be something more complicated. Calm. So that would mean this angle here has to be x, and now the diagonals add up to be each other. 2x. X plus x, so 2x has to equal 180. Agreed? Okay, shall we do E? I think we should. So try and draw E. And as you're drawing it, have a look. So we're gonna do that. And again, I don't think it's overly complicated, but it gives you some clues. It's even got a word there. Confident that they have actually solved this one. Okay, so got a few shaking of the heads, got a couple of people putting their hands up. And it's not about the actual solution here, peeps. It's about how we start. All right, so we're looking. The first thing that I look at is I go, all right, I can see there's a tangent. So I'm looking at the rules that involves tangent. I also clearly notice I've got not only a 4-sided figure, so there's definitely a cyclic quad there. What else is there? 2 triangles, okay? Now, haven't we got a theorem with a tangent and a triangle? So look for that one and then see, can we apply that? We've also got a straight line as well. And the x is outside, but we're sort of going, what's going on? So look at your tangent chord theorem. Do I have to cut it out and put it up here? I will. Worked it out. So, I mean, looking at this, and this is where you can change this around a little bit. And I told you I love my board. I love my board. Okay, so you can make that, and you can turn this with your bit of paper that you've got. How can I use this diagram? Can I use this 47 and work that backwards? So what other angle is 47? BC, yep, BC, and I'm going to say, put a point here, and I'm going to call that T. Right? So this angle here has to be the same as this angle here, agreed? 47. Well, that's great, but it's not helping me find X. So in my mind, I'm going through and I've used the tangent thing. You can go on and do the other ones if you want. I've used the tangent thing. What else is there that I haven't used that maybe it might help me? Exterior, but also haven't we got cyclic quad? Yeah. So this angle here, we know has to be, as Rian said, excellent, 180 minus 109. So we know that that is 71. And now, Charlotte, what did you mention before? Straight line. Walking in a straight line. We have got that all of these must add up to be 180. And so it's like, okay, fair enough. But it was what we did before, right? Look at what clues were in that diagram. Look at your circles and see what ones can help us. Feel free to rotate your paper to match it up. So I was a bit sloppy with this bit, not saying angle, whatever, but people should be able to follow that along. All right, so that's pretty much, actually we've got one more little section with just short, sharp, shiny, cyclic quads. Okay, question 4. So instead of saying find, oh, don't do that face. Instead of saying find the value for x, it's just saying, is it a cyclic quad or not? Right? So what did we say? It is a cyclic quad if the diagonally opposite angles add up to be 180. So it's this simple. Is 107 plus 73 equal to 180? Yes. So that is a cyclic quad. On your sheets that you have in front of you, you've got one more thing. So this comes from your angle subtended by the same arc theorem. Yeah, it basically fits into a cyclic quad. So is this fitting? That one? Yep, it is a cyclic quad. What about this one? Do those two add up to be 180? No, so it's not a cyclic quad. Like, it's that simple. Still making a face? Yeah, exactly. Take it every day. What about D? It's a rectangle, right? 90 plus 90, last time I checked, added up to be 180. So yes. What about E? Yes, because we've got a straight line here, so 180 take 113 gives you that, and then obviously those two do add up to B. What about F? Why no? Doesn't look like it. If I said to you, I made a symbol for VO. What does VO mean? Vertically opposite. Okay, so if that's 80, then that has to be 80. Right? These are diagonally opposite. Is 80 plus 50 equal to 180? No, so bang, it's not. Okay, so now we're going to go into, so we went backwards a little bit. Now we're going into the geometry that's going to include circles and, you guessed it, and some cyclic quads. So things like this are going to come our way. We ready? So heading, exercise 3G3. We're going to start. Prove that a parallelogram inscribed in a circle is a rectangle. Oof. Prove that a parallelogram inscribed in a circle is a rectangle. So the first thing we have to do is, well, it's going to be a bit hard because you're going to try and draw a parallelogram. So parallelogram, they have to be equal lengths there and there. So we draw one, and it's really hard. Like, again, this is one of those challenges. I'll give you $50 if you can draw a parallelogram in a circle and make sure that it's not a rectangle. Anyway, we have to prove it. So we're allowed to assume here that this quadrilateral ABCD has the properties of a parallelogram. So look at your doodads. And what do we know about our parallelogram? What's some of our properties of a parallelogram? Okay, so I think that there are just oodles of different ways that we could do this, but one of the things that someone just called out from the class when they looked at the properties of a parallelogram, they said that the opposite angles are equal. So we would start by saying, we could say well, I'll leave you the proof, but if we said let that one be alpha, then we're saying that that one is also alpha, aren't we? Because it's a parallelogram. So let's write that down. So let angle BAD, BAD equals alpha. Therefore, angle BCD equals angle BAD, which is alpha. And why were they equal? Because it's opposite angles para. Again, you can write parallelogram, you could write opposite angles of a parallelogram. Are we happy with that? Now, we want to prove it's a rectangle. I guess we have to have an idea. What makes a rectangle a rectangle? All angles are 90 degrees, we agree? So would you be happy that if we could prove that alpha and alpha, well, alpha, sorry, is 90 degrees, we're pretty much there? So I can say that. Why? Think about the topic we've just started. It's a cyclic quad, is it not? Because all four edges touch the. So we can also say that angle BAD plus angle BCD has to equal 180 because it is in fact a cyclic quad. Agreed? So therefore alpha plus alpha equals 180. Last time I checked, that means it's 2 alpha equals 180. Therefore alpha is. And if we really wanted to go in your face, we could say, well, that would be the same as if we had B to beta for the opposite angles. We happy? And you finish that off nicely, therefore it's a rectangle because we've got the opposite sides are the same as well, being parallelogram and then 90, huzzah, rectangle. We good? But remember, what did it come from? We started with it's a parallelogram. So that's a key word in the question. How did we use that? And then the next thing we said was, well, I can see it's a cyclic quad, like you did before if you saw it was an isosceles triangle. Use the properties of that. Agreed? Let's do the next one. ABCD is a cyclic quad. Now, what we're not going to do is draw it to make it look like a rectangle or a parallelogram. So how do we do this? I sort of go little here, and then I'm not going to make it parallel on this side. Deliberately, I'm going to go maybe like that, make it bigger. Agreed? So then we're not assuming things that we shouldn't. Oh, that's a bit curvy. Shall we make A here? Yeah. Okay, so A, B, C, D. Now, the other thing, people, when I do some of these diagrams, I don't just draw it once. So if I can't get something, sometimes I just redraw the diagram, do a little bit differently, or not picking on Danny here is very small, but I would make it, I'd draw it bigger so I can see things. This is if I can't get it straight away. All right, so now we're going to deal with the rest of it. We've drawn that it's a cyclic quad. Huzzah. X is any point on the diagonal CA. Well, let's connect C and A together. We've got that done. So we want to put X somewhere. Where do you want to put X? Tell me when to stop here. Okay, so we're putting X here. XY is drawn parallel to CB. And we go, well, where's CB? So CB is here. So that means we've got this line going through X here, okay? So I'm just going to, you look at me and then you can see what you're going to draw. So we've got a line that's going through here. It's parallel to CB. It meets AB at Y. So we just need that bit there, do we not? Oops, that made it worse. So we're going to do that. This is now Y, and it's parallel. So make sure that you put your parallel bits in there. How are we going? Not so bad? I mean, this started off, I saw your faces when I was reading it. It's like, what? Looked like a whole paragraph, okay? XY is drawn parallel to CB to meet at Y, and XZ is drawn parallel to CD to meet AD at Z. So we're going to go, it's parallel to here, parallel, parallel, Z. Yes? And what is it that we want to do? We want to prove that X, Y, A, Z is a cyclic quadrilateral. Now, what do you have to do to prove that it's a cyclic quadrilateral? The opposite side, opposite angles, diagonally opposite angles have to add up to be 180, or the crisscross theorem. Now, that has got a diagonal there. I try to do it without that crisscross first because it just adds more complexity, but I'm more than happy to use it if I have to. What do you think is going to be our saviour here? We've got parallel lines, and can I ask, do you see another cyclic quad? Yeah, I mean, the fact that they told you here is a cyclic quad is going to help you with the knowledge that in that big cyclic quad, the opposite angles add up to be 180. So, fiddle, and then we'll see how we go. Right? Shh, hello? I just said I want to use my parallel lines. So I just put this here. You could have started at the top if you wanted to. Maybe we should have done that top and work our way down. But anyway, I've gone down. I want to work my way around. How can I use my parallel lines, kids? Look. Corresponding. So that's alpha. So is that. And you go, okay, well, now what? Well, look at the big picture. What is A, B, C, D? It's a cyclic quad. Yes. Hang on. Let's use our cyclic quad. Sammy, what do we know about the angles of a cyclic quad? The diagonals add up to B. So, look at the big cyclic quad. This is 80. Oops, that's not 80. That's alpha. What's this then going to be? Yes? 180 minus alpha. I've got parallel lines. So what's this angle? Why? Because it's corresponding. And, hello, these diagonals add up to be 180. Therefore, what do they call it? Yeah, X, Y, A, Z is a cyclic quad. Peeps, it started with, how am I meant to prove that something is a cyclic quad? Right? The easiest one is to prove that the diagonally opposite angles add up to be 180. So we let one of them be alpha. Now, I'm regretting. I wish I'd done the top one, but anyway, I didn't. I went alpha at the bottom. How am I meant to get here? Well, I'm going to go around. I don't know what's going to happen. I had parallel lines. Let's use them. Okay? Because hopefully I also realised I had a bigger cyclic quad. So alpha, I'm happy that that's alpha because it's corresponding, and that was the bit I think some people didn't see. Cyclic quad, it's in the question. Use it. Diagonally opposite angles, 180 take, and then we've got parallel lines again. Huzzah! They add up to 180. Okay? Okay, so we've got ABC as our isosceles triangle in which AB equals AC. So when we draw this, let's try and not make it look like an equilateral triangle. Let's make it definitely isos. AB equals AC. So we happy? Oh, it's not in a circle. Thanks. I'm just going, I just read it as it's inscribed in a circle. My God. I think I was just excited to draw a circle. Sorry. I was just excited to draw a circle. A, B. I know. Crazy. A, B, A, C. I'm very tired. I went to the football yesterday.
Who do you support?
It was Thomas, tell him that. All right. The angle bisectors at B. So, what's an angle bisector? Cuts in half. Meets the side. So, we're going to cut that in half. And we're going to put dot, dot. Okay. And at C. Now, can I put dot, dot, or do I have to put a different? Why is it different? Same, because as isosceles, and so those bottom angles, because they are isosceles, they are the same. Anyway, the angle that cuts B at X and C at Y. Okay, show that B, X is a cyclic quad. Well, I think we've proved it. Haven't we proved this one? So because these are angle bisectors, I guess we're going to go. We won't write this one up because they can't be stuffed, but we've gone dot dot. That's what we talked about, that these two are also going to be. Sammy, we right? What are you doing? So if you had put these as cross, you have made this a very difficult problem. The fact that we knew straight away that this also had to be dot and dot. Why? Because it was an isosceles triangle. Okay? So that made these be the same, and that's what we'd write up. And then if you look at your cyclic quad things, we've got this one that goes, if we have that angle equals that angle, then it's a cyclic quadrilateral. And I believe we have that, do we not? No. No, it can be either. All right, that's it. Trapezium has equal non-parallel sides. Let's have a think about this. I think I want you to shut your laptop. Are you doing this? Okay, I apologize. My bad. A trapezium has equal non-parallel sides. So, shh. Hello. We've got our parallel. This one is going to be parallel. I'm going to draw here. Now, the non-parallel are these ones here. Now, I could draw it here, I could draw it here, or I could draw it out. What do we want? You want out, okay? So I'm going to draw it out. They're the same. Pop that in. And these are parallel. This one is sort of hard. Now, prove that the trapezium is a cyclic quadrilateral. Yep, so people are going, isn't this co-interior? It's like, okay, if that's alpha, this is 180 take alpha. Agreed. But then what happens? What has to be equal? We're a bit stuck now because we can't go anywhere else. And so the example for this one is that sometimes when you are stuck, you are allowed to, and it's only if you're stuck, you are allowed to draw stuff. Draw stuff. So you're allowed to add a line. Right? Now, where do you think if we added a line it might help? So what if we did this? And we had that this line was parallel to this one. We're drawing it in so it's parallel. Now, again, did I expect you to know that straight away? No. This is now a little weapon that you have in your tool belt, but you only use it if there's nothing else that you can do. All right? Pop that in. Now, this was parallel to this, correct? This is parallel to this. What shape does that make it if two pairs of sides are parallel? It's a parallelogram. And now, well, what does that help us do? Does that mean that that's alpha? And what are we heading towards, by the way? We're trying to prove cyclic quad. So we're trying to prove that the diagonally opposite angles add up to be 180. Oh, and by the way, because this is a parallelogram, not only is this parallel, isn't it the same length? Oh, hello. Oh, you said that. So it's an isosceles triangle. So this is alpha. What makes this? 180 take. Oops. So this is now 180, take alpha. And because we've got an isosceles triangle, this is now 180, take alpha. Hello, diagonally opposites add up to 180. It's a cyclic quad in your face. Okay, so hopefully what you have on your diagram, it's a parallelogram. So have you put, you also know that they are the same. Now, I guess this is where you might be now going, there's too much information, depending. So do you know that, you know, you might not put everything on, but you've registered that it's happening. We've got, center O, radius OA, nice. BA is produced, prove that DO. Okay, so we have to connect that. I'm actually going to do it in the same color so it looks nice. Oops, now as soon as I connected that, what should I do? Right, it's the same as, oops, go back to green. It's the same as that. So yeah, back of my mind, we've got isosceles. Now, prove that DOCB is a cyclic quad. Now, I think because someone just said isosceles, I want to use that. So I would start by sticking an alpha there. What are you forced to do next? Like, that's an isosceles triangle. What else would you then do? Right, so this is now alpha. Pardon me? Yes, thank you very much. So this one here is 180 minus alpha. Then the other corner, Rian, this is your subject, right? Then that is also 180. Why, my friend? Why? Because it's a parallelogram. Opposite angle, diagonally opposite angles. 180, take alpha, and you go, oh, now what? We'll go back. It is, you had to prove that this is a cyclic quad, so you had to go, oh, the opposite angles add up to be 180. Now, sometimes people keep going onward and onward when they don't realize they've actually already finished the proof. So keep in mind what it is you're trying to prove and make sure you're, okay, yeah, got that. Also helps you to know where you're heading. Shall we write that one up? A couple of people in the room are putting their hands up and saying, can you come and read because we did it slightly differently. Some said we did it differently, but we get it. It's the same. So fantastic. You're getting to that point where you don't have to do it exactly the same way. Some of you might even have a better short, don't be too short, but better way. And we'll just draw number 6 together. I won't do it we won't finish it on the board. You can, and I think I will get somebody to come up and write their solution, which would be fantastic. But if we all have a similar diagram, that would be nice. And I know I asked, but would anyone like to come and draw the diagram? Oh. I feel like we've done this before. But we've drawn 2 parallel chords, haven't we? Oh, do that one again. Oh, yeah. Okay, 2 parallel chords. Again, I like to do them a little bit differently. A, B, C, D, parallel, put them in. Center O. AD and BC meet at E. Prove that AEOC is a cyclic quad. Oh, that was bad. So we're playing around with this and I left you to it, and I hope what you've recognised is you've got parallel lines, yeah? Hang on, no. Can't use the, so Michelle was just saying, oh, EOC is double this because angle at the centre. Now, angle at the centre, they actually have to be on the edge of the circle, right? So what you have spent the last, and it should only be maybe 5 minutes, maybe less, but you're going through and you're sort of going, all right, I get it. To prove that this is a cyclic quad, if this is alpha, I have to somehow prove this is 180, take alpha. You're going around, it's just hard to connect things, would I agree? So there's one other way that we can prove a cyclic quad. What's the second way? Yep. So that's the bisecting thing. So if I draw this to here, Michelle, even though she's grumpy with this topic, will now go, love it, love it, love it, because the center comes into play. I want you to look at your theorems. And by the way, before we saw the center, was there another theorem that you could see? Angle subtended by the same arc, correct. So now I want you to look at any of your theorems that use the center. Oh, I guess I've drawn it on the board here. This one, if this is 2 alpha, doesn't this mean that that's alpha? And I want you to be really clear about this. So put your pens down. Put your pens down. Grab your 2 fingers. And I want you to put them at these points here. So at home, putting them here, putting them here. And then you're taking them to the center. And then from the same points, you're going out. Oops, that moved it. Same points, you're going out. So that's what you can do on your diagram. Sorry for those at home. But you're going here to here and here to here. Agreed? So is everyone happy that if this is 2 alpha, then this is alpha? Now what can you do? Okay, angle subtended by the same arc, that would mean that is alpha. And what are we trying to get to? We're trying to get to so that maybe this is 2 alpha. You are 1 step away. We've used the angle subtended. We've used the angle at the center. What haven't we used? Parallel lines. So people are calling it out. I love it. Can we see? Can we see alternate? Now again, if you weren't using the fact that you go, hang on, I've got parallel lines there and I haven't actually used it, surely they could be of some help. Sometimes there are things that are red herrings and they don't pan out. In this case, we're going, can the parallel lines help? So look for them. And we go, okay, well, that's alpha. Remember, what are we now trying to prove? To prove that it's cyclic quad, we're going for this bit here. So if that's 2 alpha, we want to prove that's 2 alpha. So we're trying to end up, sometimes I shade the angle that I'm trying to get to. One of my favorite theorems can finish you off here. Exterior angle of a triangle means that that's 2 alpha. Bang, we're done. Keep a straight face, Michelle. If you had persisted in sticking with, I've got to prove that the opposite angles add up to be 180, and you just stuck with that, and you didn't try and change your tact, okay? You would have been there for ages. You might have eventually got there, I don't know, but you keep going. So what you have to do is not be shy to change it up and go, well, this didn't work. Let's try something else, okay? What was the other thing? Make sure you use all of the things that you've got on the diagram to their full advantage. The fact that we had center of a circle and it wasn't useful to us until we connected that line. And then, oh my God, now I can use some theorems that have got the center of a circle. All right, homework. I understand some of you have got your methods things, but again, I still have, and it's tomorrow. Shall we just say, draw 7, see if you can do it, and see if you can do a little bit of 8. Is that reasonable? You'd still owe me a little bit then on the weekend.